Hello again, everyone, and welcome to part 5 of my Block 74 Apollo Guidance Computer series. Today's going to be a bit different from the videos we've had up until now. Previously, we've mainly been talking about the design of the Apollo Guidance Computer, the registers and kind of how they're laid out, and then we've specifically gotten into more about the Z register and the B and C register and how we're going to design the schematic and replicate that functionality. So fairly early on into this project, I had to start thinking about how am I actually going to build the real replica once I've finished all the design work. Now, you could look at breadboards and breadboarding it, and this is what Ben Eater does in his 8-bit as simple as possible computer series, is basically building it all on breadboards. Now, this has some benefits. You can reconfigure and you can kind of play around until you get things working just the way you want. But with the Apollo Guidance Computer replica, the scale is much larger. I mean, when you go from an 8-bit computer to a 16-bit computer, of course, the number of chips just there alone doubles. Your registers are twice the size. You need twice as many transceivers, as well as the Apollo Guidance Computer has more registers and the control logic is much more complicated. So if I were to use actual breadboards, we'd probably be looking at probably about 100 breadboards. And, with all the wires and stuff, it's easy to bump something, knock it out of place, and you could probably spend weeks trying to troubleshoot the one wire that came loose or popped out. So while I'm going to use breadboards from time to time to kind of validate some of the designs I'm working on and make sure that things are working as I expect, I didn't want to build the actual computer out of breadboards. Now, one thing that also is going to be a bit different from how the real computer was built is in one of the previous episodes, we talked about how the Apollo Guidance Computer used kind of bit slices. So there are kind of 4 main modules that implemented a lot of the core registers. And across those 4 registers, they would implement basically 1 bit of every single register as a slice. So you'd have all the bit 1s, all the bit 2s, all the bit 3s. Of course, because there are 4 of those modules and a 16-bit computer, each card implemented 4 bits across all of the registers in the Apollo Guidance Computer. Now, that makes it complicated to kind of design and troubleshoot and test because everything's kind of all mixed together. So what I've done is I've actually broken it into individual registers. We'll kind of design and understand each register completely, and then we'll build and test each one separately. Now, as I started thinking, okay, how am I actually going to build this computer once the time comes? And I looked at a few different options. The first is, looking at these kind of different prototyping boards that you can get like this. And this is very similar to a breadboard. It kind of implements the same kind of tracks that you can, put a chip in, solder different connections together, and build your circuitry. Now, you could do it this way, where you actually solder, or you can also use large perf boards like this and use wire wrap. So wire wrap is you have sockets that have long pins on the back. You use a special tool to wrap wire tightly around each of the pins. And that's a good technique for prototyping because you can unwrap the wire and move things around if you didn't get it right. I've tried doing wire wrap in the past, and I haven't had a lot of success with it. Other people swear by it. So if that's an approach you want to take, by all means. But I kind of like solder. I like to solder. It's permanent. And means there's time to time where I'm going to have to unsolder things and do some rework when I make a mistake. But that's kind of the approach that I'd like to take. Now, what's other nice about these particular prototyping boards is that they have this kind of connector where you can put this 96-pin VME socket on the end. And it makes for like a nice little kind of card you can plug into a backplane and a good module that you can do kind of test independently. Now, very quickly, I realized that these particular boards, they didn't have enough room for what I needed. They just didn't have enough space for enough chips to support building out a particular register on this side. So looking at a couple of different options, and the prices on boards start getting fairly high fairly quickly as they get larger and a bit more unique, and you've seen pictures of this in some of the previous videos, I designed this kind of custom printed circuit board. And when you buy these in volume of 10, they're actually quite reasonably priced. This one probably works at about $20 each for all these boards. And creating kind of a common board that I can use for building most of the computer is going to simplify things a lot. Now, some people have asked, well, why not design a custom board for each register? If I look at the design of the overall computer, there's probably going to be a good, I'd probably say 15 to 20 of these in total in order to replicate the full functionality of the computer. And designing 15 or 20 custom PC boards gets very expensive very quickly. So instead, I create this more generic card that I can use to build a wide variety of different pieces of the computer. So because we're, a lot of the core registers, we've got kind of space here along here for 4 of the D register chips. I've got room for up to 4 of the larger bus transceiver chips. And then we've got room for, the service logic kind of up here on the front. Now, some of the other cards, once we get beyond registers, are going to have room for either memory chips or EEPROMs to implement control logic. So I've got the flexibility to add up to 5 of those larger chips here. And then in case I don't need any of those larger chips, I've provided some additional pads for other chips that I can add as needed. By implementing these on this common card, I can provide ground. So if you look at all the 74LS series, the kind of the last pin on the left is ground. So that'll be, for the smaller logic, the 14-pin chips, that's pin 7. For the larger 16-pin chips, that's pin 8. So that I can kind of pre-wire that for ground and then provide pre-wire for power as well. And then I've got, of course, the filter capacitors for each and every chip and others to kind of support functionality that I'm going to commonly need. So I've got 16 LEDs along the front that I can use for displaying the contents of the bus or register. I've got some resistors here, space for resistors to provide current control through those LEDs. And then at the end here, I've got room for my 96-pin connector that makes it easy to connect each and every one of these cards onto a common backplane. Now, as I start kind of looking through and allocating, okay, each of these connectors has 96 pins, and you'd think very quickly, oh, 96 pins, that's lots. But you run out fairly quickly. You look at the write lines, there's 16 right there for the write lines. The AGC has probably a good, 80 different control pulses. Now, not all the control pulses need to be present on every single card, so they're not all present on this bus. But then you distribute power, ground, clocks. You start very quickly running out of the 96 pins. So far, I've been able to kind of shoehorn all the functionality that I need on the backplane into those 96 pins. But there are certain scenarios where individual cards really need to talk directly to one another. So there's some commands, for example, where I can load the X register or transfer data between registers that are direct. So they don't go through the write lines. So most data transfer between registers is, I pull data off the write lines into my D registers, and then I write them out through the transceivers back out onto the common bus. But there are several instructions where I need to transfer data directly between, for example, the A register and the X register, for example. There's others between the G register and other registers in the system that need to occur directly. So I've created this, added this additional 34-pin connector up here that allows me to connect cards together in order for them to transfer data instead of consuming pins on the bus for each and every go to every card that just aren't necessary. So that's kind of these particular cards. This will be a future X register. And then as I start to build them up, kind of go through a process of building them. So here's a register card that I'm starting to work on. So far, I've just soldered on the chips, and that's kind of where I like to start. You get all the different logic chips on. And then from there, you start adding additional components. So this is the Q register. This is actually the next one I'm going to be building. I've added the 16 LEDs, the bus resistors, all of the capacitors, and then card connectors for both the 34 pin and the 96 pin VME connector here. And then after that, actually wiring everything together, it looks like this. So this is my Z register. It's actually already, I've validated and tested its functionality. So this one's actually ready to go. I've done a bit of color coding with my wiring to kind of keep track of things. So I've got the blue, which are basically the data bus. So I've got basically from the common bus connector here, I kind of run data out into the registers to load data in, and then data back out from the transceivers back out onto the bus. I've got yellow, which are my kind of control pulses that enable for example, the clock for my Z register, or the WZ or RZ signals to bring those in to either load data into the register or push data out onto the bus. I've got some red wiring, which is really just outputs onto my LEDs. And then I come to have a few black wires just for where I've had to either connect pins to ground or provide pull up different pins depending on what's necessary. That's what it looks like as a complete card. This one's probably one of the simplest ones there is, and the wiring definitely gets more and more complicated on some of the other cards. Now, by the self, it's like, okay, well, what am I going to connect them to? How am I going to bring the computer all together? Now, in the real Apollo Guidance computer, each of the modules had a large card connector that had quite a few connections that connected onto a back plane in the actual A side or B side. And those used wire wrap to interconnect all the different components across the back plane. I'll try to find a picture and attach it in, but it was a fairly complex nest of wiring on the back plane of the real AGC. What I've done is I've designed another card here, which is my backplane card. And you can see there's room. This one only has 4 connectors right now, but room for 7 connectors that each card can plug into. I've got a couple of electrolytic capacitors just for power filtering to make sure that each and every card is well supplied with DC. And then I've got a number of pull up and pull down resistors. Now, because the Apollo Guidance computer is negative logic again, on all of the kind of control signals on the back plane, I use pull up resistors so that they're always set to a 1 unless I assert them. That way we don't get any extraneous asserted control pulses between cards. And then for any of the data lines, like the write lines, and there's a few other little data lines that we carry out through all the different cards, like some of the contents of the branch registers, which are used by a number of different cards. I use pull down resistors. So I keep those at a 0 state until they're actually pulled up with data on a particular bus. So that's kind of the design of how that's laid out. And then I figure by the time this is all done, I'm probably going to need 3 of these connected together to provide the full backplane for the Apollo Guidance computer. So I've created these 2 50-pin connectors here, which I'll eventually use a ribbon cable to connect the 3 backplane cards together. This is also where power comes in. So I've got these nice little power connectors, and then I've got a 5-volt power supply that I'm using right here to provide a lot of power for everything. So I'm going to need quite a bit. This is a 5 amp supply, so it should give me plenty of juice to run all of the logic circuits that I'll need for the Apollo Guidance computer. So that's the approach that I'm going to be taking in building the guidance computer. You can kind of see I can plug in a card like this. And that's what it'll look like when it's all done, is a number of cards plugged into the backplane to provide functionality, and then some of them will be cross-connected with other ribbon cables. Now, I'm not going to go through the actual construction of each and every one of these cards, just the amount of work that it takes and the amount of wiring. If you've watched some of the other videos where people are assembling their computers on breadboards, you sometimes use a little bit of stop motion photography to kind of accelerate the connecting of all the different wires to the bus. Again, when you're looking at a 16-bit computer, every single bus connection is 16 wires. There's a lot more control, pulses, and logic, and it would be a pretty boring video of just kind of you watching me run wires, flipping it over, solder, flipping it back over, running another wire, flipping it over, soldering. So I'll kind of more as I build each and every module, I'll show some videos as we start actually testing the components and see how they start to function together. But for the next few videos, it's really going to be more focusing on kind of the design of the various different registers that go into the computer. So next one we'll be doing is the Q register, which is also known as the quick register. And that has some of the features and a little bit of a sneak peek of the Z register, and that it is a directly accessible register like the Z register, but it also manages some of the input and output bus capabilities on the Apollo guidance computer. So rather than just pushing data in and out to the right bus, I'm going to be using this for some of the I/O channels that it uses to kind of push data in and out for I/O to other devices like the display, like the DISC-key display and keyboard module for the Apollo guidance computer, and other sensors and data that comes in from, in the real thing, it would be the lunar module, but we're going to have to simulate that down the road as we get closer. As always, if you're interested in learning more and following along, please subscribe. And of course, feedback is always welcome. Always want to know how I can improve these videos and answer questions that folks might have. Otherwise, have a great day, and we'll see you soon.